Today we're going to be talking about intermolecular forces. Intermolecular forces is a really important topic in science, in all areas of science, not just chemistry, but also biology and also environmental science. Intermolecular forces, let's start by defining what those mean. Okay, so intermolecular forces, as the name suggests, are the forces between molecules. So that inter prefix means between, just like it does in any word that you see it. Intermission, interception, it means between whenever you see it. Now, if we think about what that means for a sample, let's get a sample of water, let's put on our molecule glasses, and let's expand it so that we can see the individual water molecules. So the intermolecular forces are the forces between each of those molecules, and you can see the little dashed lines that are supposed to represent the intermolecular forces in this case. Now, to make sure that this is clear, let's draw an individual water molecule and make sure that we understand that these are not the forces that hold that water molecule together. Those would be the covalent bonds that attach the hydrogens to the oxygen. Those, if we had a name for them, would be intramolecular forces, the forces within the molecule. That's not usually a term we use, but just to contrast it with intermolecular forces, that's what that would mean. So today we're talking about the forces between molecules in a given sample. This is a list of the 5 intermolecular forces that we're going to talk about today. There are others, and we're going to talk about that, but you can kind of mix and match lots of different kinds that we'll see later. But let's just talk about these 5 for now. Ion-ion interactions, we're going to start at the top of the list. This is the mutual attraction of oppositely charged ions. The example I have here is sodium chloride, but any ionic compound would work here because all ionic compounds exhibit these interactions. These are actually just another name for the ionic bonds that you learned about first semester. Okay, so if we take our salt shaker and we magnify it some more so we can see the little cubic crystals, then if we put on our molecule glasses again and we look at the individual crystal lattice, the sodium ions are shown with these purpley blue spheres, and the chloride ions are shown with the traditional green color that chlorine is usually shown in. You can see that the ions alternate, right? Sodium chloride, sodium chloride, sodium chloride, and they are held together in this what we call crystal lattice by these very, very strong ion-ion interactions. Now let's move on about dipole-dipole interactions. Dipole-dipole interactions, let's put up another model. This is hydrogen chloride. And this is several, let's see, for 12 hydrogen chloride molecules, where hydrogen is shown in white and chlorine is shown in green, and there's a covalent bond that connects the hydrogen to the chlorine. You can see the little dashed lines. Those are supposed to represent the dipole-dipole interactions between each of those molecules. So these dipole-dipole interactions are the attractive forces between polar molecules. Okay, so that's what the word dipole means in this case, is a polar molecule. And hydrogen chloride, that molecule itself is polar. Each HCl molecule is considered a dipole in the quote dipole-dipole interaction. We're going to come back to that in a minute, but let's for now review polarity. Okay, this is something you learned last semester, but it's really, really important for this topic. So we're going to go back over it one more time just to make sure everybody's clear. Now, this is my hydrogen chloride molecule, and a polar bond, let's start with that. A polar bond is a covalent bond that has an unequal distribution of electrons, and that's because one of the atoms that's sharing is not sharing equally. He's pulling the electrons more toward himself, and that causes a distribution, a separation in the electrons, an unequal distribution of electrons, which causes an unequal distribution of charge. In this case, chlorine is more electronegative than hydrogen, and it therefore pulls the shared electrons toward it, creating a polar bond. We represent polarity, polar bonds, using these arrows. Okay, so the arrowhead is drawn in the direction that the electrons are being pulled toward chlorine, always toward the more electronegative atom. And as a reminder, there's a little plus at the other end to remind ourselves that because hydrogen has lost some of those electrons, he's partially positive. So that's like a little plus sign. Now another way to denote a polar bond is with these partial charge symbols. This is a lowercase letter, it's a lowercase delta, it's a Greek letter, and in this case it means partial. So the delta plus means partial positive charge, and the delta minus is a partial negative charge. Now we have another representation of hydrogen chloride which comes from your book, which I know is not nearly as cool as the one I drew on the previous slide, but that's okay. On the left is the Lewis dot structure, which shows the delta plus and delta minus. On the right-hand side is what I wanted to draw your attention to, which is a ball and stick model. And surrounding that ball and stick model, they have drawn what is called an electrostatic potential map. And what really matters there is that I want you to know that you can see there's a blue color on the outside. That blue color represents the partial positive charge on the molecule. And the red represents partial negative charge. And so that's kind of always true when you see an electrostatic potential map. The blue represents positive and the red represents negative, and we'll see that more and more. Now, view electronegativity because it's kind of important when it comes to polarity. So remember that electronegativity is the tendency of an atom to draw shared electrons toward itself, which means that fluorine, being the most electronegative element on the table, if it is involved in a covalent bond, it will actually attract those electrons toward it, and it will therefore be partially negative. Now, the table shows you that the tendency for electronegativity is that it increases as you move up and to the right on the table. Now, I don't usually remember it that way. I just remember that fluorine's the most electronegative, and it's in the upper right-hand corner. And I remember that francium, which actually isn't on your table, it's just below cesium normally, is in the lower left-hand corner. It's the most electropositive on the periodic table. So that's usually what I remember, and you're always going to have a table with you anyway, so as long as you remember that fluorine's the most, that'll help you with the trend. Electronegativity increases as you move up and to the right on the table. Now what I really want you to remember, you don't have to remember those numbers like 4 and 3.5 and 3. You don't have to remember the actual numbers, but I do want you to remember the trend. So the general rule that I want you to remember regarding electronegativity is this: fluorine is the highest. Oxygen is next, but see, oxygen's right next to him on the table, so it shouldn't be too hard to remember. Nitrogen follows oxygen, and chlorine and nitrogen are essentially the same. All the rest are after that. Okay, so I do want you to remember that second line there. Fluorine is greater than oxygen, is greater than nitrogen, is similar to chlorine, is greater than the rest. Remember that. Another little tidbit I want you to remember is that carbon and hydrogen have very similar electronegativities, which means that when you have a CH bond, that bond is nonpolar. Okay, now this asterisk is because that is a tiny white lie, and I will fix that later at the end of the semester, but we'll come back to that later. For now, remember that they are essentially the same. Okay, now let's move on. This is a picture from your book, and I wanted you to see this because I want you to think about polar bonds as being partway between a nonpolar covalent bond, which has no difference in electronegativity, there's no difference in charge, and a full ionic bond, so something like sodium chloride, would be on the far right. You should think about a polar covalent bond as being partway between those two, because it really is. Okay, it involves partial charges, and it's really kind of somewhere between those two. Review along the same lines shows these ball and stick models. So if we think about a nonpolar covalent bond like chlorine, Cl connected to another Cl, there's no difference in electronegativity because it's the same atom, therefore that is a nonpolar bond, a nonpolar molecule. If we think about the other extreme, where we have sodium and chloride, they've drawn a ball and stick model. That's kind of unusual to see that stick when there's not really a covalent bond there. But what I want you to really see here is that there's a whole lot of that red color on the right-hand side of that molecule or that compound, and there's a whole lot of blue on the left-hand side where the sodium is. And if we think about between those two, a polar bond like hydrogen chloride, it's not quite as red, it's not quite as blue. Okay, so it's kind of partway between the two. Now, we're going to review polarity with 3 molecules. We have hydrogen chloride, we have carbon dioxide, and we have water. Because I want to make sure everybody understands the difference between a polar bond and a polar molecule. Okay, we have our 3 molecules here: hydrogen chloride, carbon dioxide, and water. Hydrogen chloride is shown here, and I'm drawing the dipole where the electrons are pulled toward chlorine. There's a partial positive on the hydrogen side and a partial negative on the chlorine side, just like we looked at a few minutes ago. Hydrogen chloride itself, having just this bond, is polar. And so that's why it's our example for dipole-dipole interactions. Now we have CO2, and this one's a little bit different. So carbon and oxygen have a difference in electronegativity. Carbon is more electropositive, oxygen is more electronegative. So the arrows are drawn out toward oxygen. Now, in this case, the dipoles cancel out. They pull out equally in opposite directions, which means that carbon dioxide as a molecule is nonpolar in spite of having polar bonds. Now, I want to make sure everybody understands that there are two possibilities for getting a nonpolar molecule. You can either have all nonpolar bonds, or, in this case, polar bonds that cancel out. Finally, let's look at water. Water has an oxygen-hydrogen bond that is polar because oxygen is more electronegative. So we're going to draw the arrows toward oxygen. Now in this case, water has a bent geometry. So these dipoles do not cancel, and the molecule itself is therefore polar. And this has a dramatic effect on its properties. And in the very last picture, I wanted to show you that these polar water molecules will have an overall dipole that's shown here in green. The overall dipole goes through the oxygen, so that end of the molecule becomes partially negative, and the hydrogen parts are partially positive, like I'm showing here with the deltas. These are different water molecules, and you can see that they orient themselves so that the partially positive hydrogens are toward the partially negative oxygens. Okay, so let's get back to our intermolecular forces and our dipole-dipole interactions specifically. Hydrogen chloride is shown here, and I wanted to show you that these dashed lines again represent the intermolecular force, in this case the dipole-dipole interaction. If we just look at two molecules with one intermolecular force shown, then the reason it's called a dipole-dipole interaction is because one HCl molecule is called a dipole and the other HCl molecule is considered another dipole, and hence the intermolecular force between them is a, quote, dipole-dipole interaction. One other thing I want to call your attention to is that these molecules are all oriented so that the partial positive hydrogen side of the molecule is directed toward the partial negative chlorine side of the molecule. And that always is going to tend to happen with a dipole-dipole interaction. Your book's image shown here, and even though it's not nearly as cool as mine, I wanted to include it just for fun. So you can see a generic dipole-dipole interaction on the left. This is what would happen. The partial positives would maximize their interaction with the partial negatives, and that would be more favorable than what you see on the right, which would not happen, where you see these negatives repelling each other and the like charge positives repelling each other. So what would happen is what is on the left. Now that's all we're going to talk about with dipole-dipole, but we'll come back to that when we talk about the relative strength of all of these. And let's move on to ion dipole. This one is different than the others, but I wanted to introduce it here because your book includes it in the table of intermolecular forces, so I didn't want to ignore it. We're going to talk a lot more about this one in the next chapter, however. So an ion dipole interaction, in the lower left corner is a cartoon that shows the interaction between sodium, a sodium cation, and a water molecule. And these interactions will only exist in a mixture, of course, because you have to have the ions mixed in with polar molecules. And so you will not see these intermolecular forces in pure samples, which means that you can kind of ignore them whenever we talk about pure samples. We'll talk a lot more about them in the next chapter when we talk about dissolving things, solutions. These kinds of interactions are the interactions that exist between an ionic solid when you dissolve it in a polar solvent like water. So if you make a salt solution like you see here, Now, in this case, the ion-dipole interaction is the favorable interaction between the ion, which in this case is either sodium or chloride, and the, quote, dipole, which is the polar water molecule, and hence that dashed line is an ion-dipole interaction. Now, again, you should notice the orientation of the water molecules. The partially negative oxygen side is oriented toward the sodium cation and away from the chloride anion. That's to maximize the favorable electrostatic interactions. And over here, the partially positive hydrogen atom is oriented toward the chloride anion, and of course it is oriented away from the sodium cation. This is your book's representation of the same thing with a general polar molecule and an anion on the left and a cation on the right. So a very similar idea. Now we're going to come back to ion dipole in the next chapter, but I didn't want to ignore him here, so we've included him and we'll come back to him later. Now hydrogen bonding is really important, so we're going to spend a little bit of time on this one. Hydrogen bonding has very specific requirements, and I know that you've learned about hydrogen bonding in biology, but I wanted to make sure that you understand the very specific requirements for a hydrogen bond. So this is a very strong, unusually strong type of dipole-dipole interaction. It's so strong it gets its own class of intermolecular force. And here we have X is either fluorine, oxygen, or nitrogen, and it's covalently attached to a hydrogen atom. That's why it's called a hydrogen bond. And it is the interaction between that hydrogen and a lone pair of electrons on an adjacent fluorine, oxygen, or nitrogen on a different molecule. Now, let's talk about the requirements first. Let's talk about fluorine, oxygen, and nitrogen. Okay, so why fluorine, oxygen, or nitrogen? You've probably, based on what we talked about earlier in this same discussion, you've probably figured out that it is because they are very electronegative, which is true. They are the three most electronegative elements on the table, which is why they are requirements for a hydrogen bond. But why not chlorine? Chlorine is the same electronegativity as nitrogen. And it turns out that chlorine, because his valence electrons are in the third shell instead of the second shell, chlorine's just too big. And so strong hydrogen bonds require really close proximity. They need to get really close to each other, and that provides a stronger, more favorable interaction. And chlorine's just a little bit too big for the adjacent molecule to get close to it. Nitrogen is smaller, and it works better. Now, hydrogen bonding is unusually strong. It's very important in biology, and that was the next thing I wanted to show you. This is an image that we're going to come back to in a minute, but here we have a hydrogen bond shown between oxygen on a water molecule, oxygen's lone pair, and the hydrogen on an adjacent water molecule. And you can see a ball and stick representation of the same hydrogen bond below. And on the right you see ammonia. The nitrogen in ammonia has a single lone pair which can hydrogen bond to a hydrogen on an adjacent ammonia molecule. Now, a little bit about biology. Hydrogen bonding is the force that stabilizes the three-dimensional structure of DNA and proteins, and so it's really important in biology. Now let's get back to our requirements. This XH group, that is called the hydrogen bond donor. So the group that contains the hydrogen is called the donor. It donates the hydrogen bond. The group that has the lone pair of electrons is called the acceptor. And every hydrogen bond has one donor and one acceptor. And you do need to know that. We're going to talk about that in a few minutes because it has some significant implications in terms of the strength of the hydrogen bonds. So on the left we have water. And the same picture is drawn here with the hydrogen bond between the lone pair of electrons on oxygen and the hydrogen of an adjacent water molecule. So what you can see from the water molecule is that each oxygen has two lone pairs, which means it can accept two hydrogen bonds. Each water molecule also has two hydrogens, which means it can also donate two hydrogen bonds, which is very important. It makes it very, very strong in terms of its intermolecular forces because every water molecule can hydrogen bond a lot with adjacent water molecules. Now on the right, to contrast that, ammonia has three hydrogens, which means it can donate three hydrogen bonds. However, each ammonia molecule only has one lone pair on the nitrogen, which means it can only accept one hydrogen bond per molecule, which really severely limits the amount of hydrogen bonding that can exist in a sample of ammonia. And so that really dramatically affects the strength of the intermolecular forces in that sample. We're going to come back to that a little bit later. For now, let's say we're done with hydrogen bonding and we're going to move on to the last force, which is called London dispersion forces. Now in this case we have a chlorine molecule. So chlorine is a nonpolar molecule. It is a chlorine atom covalently attached to another chlorine atom. And we know that these are nonpolar. However, the electrons move around. And what happens is electrons move, and at any given point in time they may find themselves more, that they dominate more on the left-hand side of the molecule, say, like we have shown here. And so if that happens, if you have more electrons congregated on the left just by circumstance, pure coincidence, that single molecule will develop a temporary dipole where there's a partial negative on the left and a partial positive on the right. And of course, if left by itself, that will go away because electrons will just move back. However, if there is an adjacent chlorine molecule, then what happens is the partial positive charge that develops will attract electrons toward itself, and that will induce a dipole in a neighboring molecule. And then those electrons will move because they're attracted to the partial positive end, and that will generate another dipole. And then another adjacent molecule, electrons will move there. And so it's sort of like a chain reaction, where if electrons move around, then they tend to generate temporary dipoles, which induce dipoles in adjacent molecules. We're going to talk more about that. So let's talk about this a little bit more. These kinds of intermolecular forces exist between all molecules. Also, these are the only intermolecular forces present in nonpolar molecules. So, for example, bromine, the chlorine that we have shown at the bottom right-hand corner with our green spheres, argon, which is just a noble gas, a single atom by itself floating around. And this is your book's description, which looks pretty good too. So again, on the left we have our electrostatic potential mapped over the ball and stick model of bromine in this case. And then the electron distribution will move around, which generates this temporary dipole, and it generates a dipole, induces a dipole right in an adjacent molecule. This is another picture that shows sort of a distribution of electrons with these little dots, and it's supposed to be showing sort of how these temporary partial positive charge will generate a partial negative charge in an adjacent molecule. Now we're going to talk more about these and the strengths of these later. But for now, the only other thing I want to call your attention to is how you would identify the intermolecular forces in a sample. That's going to be the next thing that you're going to have to practice. I was going to call your attention to this little flow chart, which I think you should probably use, which we will use together in class to identify the dominant intermolecular forces present in a sample.